Hello, Physics 191, esteemed professors and TAs at the beautiful Washington University in St. Louis. My name is Kyrillos Ayoub, a second year majoring in neuroscience on the pre-med track. And with me today is my partner, Chen, also a second year majoring in neuroscience on the pre-med track. Today, we'd like to present our project that explores several topics learned in physics this year, specifically collisions, elastic collisions, and inelastic collisions, conservation of linear momentum, and Hooke's law. In this model, we show a car colliding into another car, which together should collide into a spring representing the crumble zone of motor vehicles. I will go ahead and play the model now. I will play it once and then a second time where we go ahead and analyze the velocities of both cars. That was the first time. The second time, I'd like to take note of the velocity of the first car and how that compares to the velocity after the collision. I'm looking to annotate. The first time around, we see the velocity of the first car moving in this direction. The velocity of the second car is 0 as it is represented being stopped at a stop sign or a stoplight. And then afterwards, they move with the same velocity, which I will represent as V1, 2, as they collide into the tree. And again, in this model, as we will explain later, they oscillate backwards, which doesn't happen in real life. So I will go ahead and clear my drawings and play the recording of the model again. Creating the model, we drew the outline of two cars using the polygon tool. Then we created 4 circles with axles, and that was used to represent the wheels of the car. For the first car on the left, we added motors to the car. This simulation models a real-world example in which a person is on their phone and doesn't slow down while the car in front of them is again waiting on a stoplight. We see how dangerous texting while driving or being on the phone can be. Then the two cars collide into a tree. And again, the spring is representative of the crumble zone of motor vehicles now. So what exactly is the crumble zone, we may ask? The crumble zone works by managing crash energy, and it increases the time over which the deceleration of the occupants in the vehicle occurs. This prevents intrusion into or deformation of the passenger cabin. It serves as a protection of the car and the occupants against injury. So crumble zones, also referred to sometimes as crush zones, they absorb the energy of the impact, in this case, the impact of the cars against the tree, as to prevent it being transmitted to the occupants. And in specific, the crumble zones accomplish 2 safety goals. First, they reduce the initial force of the crash, and they redistribute that force before it reaches the vehicle's occupants. And then using Newton's second law, force is equal to mass times acceleration, reducing the deceleration in half would also reduce the force that the occupants experience in half.
Hey, this is Alan, as Kyrillos mentioned before. An elastic collision is really defined as a collision in which, as you can see, no kinetic energy is lost and momentum is conserved. No damage is done to the object involved in the collision, and there is no generation of heat. In the real world, really, this is usually not that common, almost impossible, really. No collision is perfectly elastic because so many forces come into play, such as friction, air resistance, and gravity. These are all things that aren't as accounted for in the model here. Unfortunately, a limitation of our model on Algodoo is that our collision partially represents an elastic collision. The model is similar almost to like a game of pool, right? And that it only offers a fairly good elastic representation. In our model, the cars remain separate ultimately. But in any collision, though, there had to have been conservation of linear momentum, represented by this familiar equation to all of us: m1 v1 equals m2 v2. But again, this ultimately can manifest itself in many ways depending on the collision that is really occurring. Our model should be in inelastic collision. Perfectly inelastic collisions occur when the objects colliding become ultimately one mass, aka they kind of stick together, right? This is represented by the momentum of the first object plus the momentum of the second object equal to the final total momentum of both objects. Kinetic energy is not conserved. Sometimes we see, smoke come out of cars following an accident because, as you can see, some of that kinetic energy in inelastic collisions is transferred into heat, and this could also have implications on fuel supplies in the cars and other potential of like excitatory parts in the car that may have smoke. So it's not always going to be from the actual collision, but a large part of the heat is from the collision. And also a lot of the kinetic energy too, in a real life, collision of vehicles, of automobiles, will be transferred into sound energy, which is something that our model also doesn't exactly account for here. Another limitation of our model is that the spring oscillates. Hooke's law says that the force of the spring is equal to the constant of a spring contact and the spring compression in this case. In reality, though, the crumple zone shown here, just to reiterate one more time, the crumple zone shown here, right over here, is supposed to be permanently deformed. A lot of cars, when they get totaled, can't really come back, right? Instead, here the cars are rigid bodies and they oscillate backwards with the spring. This really wouldn't happen in real life. In conclusion, Kyrillos and I both agreed that it was really fun using Algodoo. We had a really good time playing with different ideas and different models. We considered the crush zone to be very interesting because it's pretty applicable, but like with Kyrillos being an EMT, right? And both of us being aspiring physicians and clinicians, I'm interested in emergency medicine, so I will have to also ultimately, it's a reality that I'll probably be seeing patients who did come from car accidents that had very similar models to as we described today. And with car accidents being really dangerous and with emerging new technology, this model is something that's like really heavily and increasingly tested ultimately for the safety of people. And that's really where physics and engineering really comes into play, is like safety, and we really want these models that like real physicists that obviously have like more hardcore models than we do, but this is just one step in learning more about what physicists do every day and what engineers do every day to really support humanity almost. So yeah, thank you so much for watching our presentation today. We really appreciate it. I guess there's no really Q&A session, but if you have any questions, I guess reach out to Kyrillos and I. We're pretty into it. Our emails should be searchable on WashU's directory. So yeah, let us know.
Yeah.
Thank you so much. Take care.